Adhayan Academy is dedicated to bringing interesting lectures with solved example questions on a variety of subjects with critical concepts. For topic-based worksheets with detailed solutions, go to our website, adhayan.com. If you enjoy our videos, please like, share, and subscribe. Now let's solve question 3 from year 2014, variant 4.2, MJ, question number 3, C and D. It says that the acid dissociation constant of ethanoic acid is 1.75 times 10 to the power minus 5. Explain why this value of Ka is much larger than that of ethanol. Well, we know that the greater the acid dissociation constant, the lower the pH value, and therefore it is more acidic, much more acidic. So this tells us that ethanoic acid is more acidic than ethanol. Now, why is that so? Well, first, let's draw out what they look like. So, now that we have the structures of ethanoic acid and ethanol drawn, let's understand why ethanoic acid is more acidic than ethanol. Well, for the first point, ethanoic acid has fewer number of electron donating alkyl groups than ethanoic acid. It has only one alkyl electron donating group, whilst ethanol has 2 of them. So since ethanol has more electron donating alkyl groups, which transfers their electrons to the oxygen atom, this causes the charge density of oxygen atom to be greater. So since it's more negative, the hydrogen ions will be more attracted to it, and therefore it will not want to easily leave to form H+ ions. And so since fewer hydrogen ions are released by ethanol, it is less acidic. And since there is only one electron donating alkyl group in ethanoic acid, this oxygen in the compound is not as negatively charged as the one in ethanol. That is why ethanol is able to release fewer hydrogen ions and ethanoic acid is able to release more hydrogen ions, causing ethanoic acid to be more acidic. There is another reason why ethanoic acid compound is able to release more hydrogen ions than ethanol, and that is because it has an electron withdrawing carbonyl group, which is this group, the carbonyl group. What does it mean when I say an electron withdrawing group? Well, it means that this oxygen here attracts all of the electrons from the compound towards itself, making it the most charged in the whole compound. And this causes the OH bond to weaken. And since it weakens, it is able to release greater number of hydrogen ions. And since greater number of hydrogen ions are released, ethanoic acid is more acidic. So let's write the answer. We can say that ethanoic acid has a smaller electron donating alkyl group. Thus, its anion, meaning CH3COO minus, is more stable than the ethanol's anion of CH3CH2O minus. Hence, it is more acidic. Now, in this answer, we've talked about the first concept of how to understand why ethanoic acid is more acidic than alcohol. There is another way to write this answer where we will be talking about how the electron withdrawing group weakens the OH bond, causing the ethanoic acid to have a greater acidity. So if we erase this answer, let's erase this answer and rewrite the other version of this answer. We can write that ethanoic acid has an electron withdrawing carbonyl group which is in close proximity to the OH bond, causing the OH bond to weaken and release more hydrogen ions. That's it. That's all you have to write. Both those answers are correct. Moving on to the second part, they ask us why the acid dissociation constant value of ethanoic acid is much smaller than that of chloroethanoic acid. Here we are dealing with an example where both of the compounds we are comparing are acids. So let's draw ethanoic acid again, and let's draw chloroethanoic acid. This is an interesting example where in ethanoic acid we have only an alkyl group and a carboxyl group, and in chloroethanoic acid we have a halogen group. Halogens are usually electron withdrawing groups. So here again, what will happen is all the electrons will pass to the chlorine atom in the molecule, and this will cause the OH bond to break. Thus we can say that the OH bond in chloroethanoic acid is much more easily broken than that in ethanoic acid. Therefore, we can write the answer to be chloroethanoic acid has an electronegative. You don't have to write electronegative, but I just wrote it. electronegative electron withdrawing chlorine atom. Now you have to write the electron withdrawing chlorine atom part. That makes the anion ClCH2COO- more stable than the anion of ethanoic acid. Now you can write the anion, or you don't have to either, but I'm just going to write it here, CH3COO-. Hence, it is more acidic. For part 2 of C, we've been asked to calculate the pH of 0.1 mole per dm cube solution of ethanoic acid. So ethanoic acid is a weak acid. So we need its acid dissociation constant value. We were told it was 1.75 times 10 to the power minus 5. Okay. So first, let's calculate the hydrogen ion concentration is Ka into weak acid, which will be 1.75 times 10 to the power minus 5 into 0.1, which will give us 1.32 times 10 to the power minus 3 mole per dm cube. And pH will be minus log H plus, which is where you can just substitute this value into the H plus portion of the equation, where we will get the pH of the solution to be 2.88. Moving on to part D, 20 centimeter cube of 0.1 mole per dm cube sodium hydroxide was slowly added to 10 centimeter cube solution of 0.1 mole per dm cube ethanoic acid, and pH was measured throughout the addition. Okay, so part 1, calculate the number of moles of sodium hydroxide remaining at the end of the titration. Okay, now since we have been told ways to find the moles of both sodium hydroxide and ethanoic acid, we can clearly understand that this is sort of like a limiting reagent kind of question. So to proceed, let's first find the moles of NaOH initial, which is 2 times 10 to the power minus 3 moles, and the moles of ethanoic acid, which will be 1 times 10 to the power minus 3 mole. Now, I found this by doing moles equals to concentration into volume by 1000, because the volume was given in centimeter cube. Now, since we know that this is a limiting reagent kind of question, we must write about the reaction between sodium hydroxide and ethanoic acid. So let's write it somewhere here. NaOH plus CH3O2H will provide CH3CO2Na and H2O molecules. So we can see that sodium hydroxide and ethanoic acid react in 1:1 molar ratio, and we can see already that sodium hydroxide is in excess. So how much more do we have? So NaOH excess will be 2 minus 1 times 10 to the power minus 3 moles, which is 1 times 10 to the power minus 3 moles. And now we have to calculate the hydrogen ion concentration after the addition? Well, after we add two solutions, one part of it was sodium hydroxide and the other part was ethanoic acid. So now the volume of the solution has changed, and so the concentration of the excess sodium hydroxide will change. So we can find it to be sodium hydroxide concentration to be moles per volume, which is 1 times 10 to the power minus 3 into 30 by 1000. Well, it is 30 because 20 centimeter cube and 10 centimeter cube were added to form a 30 centimeter cube solution. So to this we get 0.03 mole per dm cube. And since hydroxide ion and sodium hydroxide are in 1:1 mole per ratio, we can say that the hydroxide ion concentration is also 0.03 moles per dm cube. In part 3, using the expression of Kw and our values in part 2, we have to calculate the hydrogen ion concentration and the pH of the solution at the end of the addition. Okay, so Kw is H plus OH into OH minus concentrations, which is 1 times 10 to the power minus 14. So H plus minus 14 by 0.03, which gives us 3 times 10 to the power minus 13. So pH is equals to minus log H plus, which will give us 12.5. That is our answer. Now, in part 4, we've been told that on the following axis, sketch how pH values change during the addition of the total 20 centimeter cube, 0.1 mole per dm cube sodium hydroxide. Oh, so they want us to draw the titration curve of this reaction. So we know that in a titration curve, we have to draw how the pH value of the solution in the beaker changes. And from the instructions, we know that ethanoic acid was within the beaker. So what was the initial pH of the beaker? This is the pH we found in C part 2, which is 2.88, because here the solution was also of 0.1 mole per dm cube. So we can just say that at the beginning, when there was 0 sodium hydroxide solution, the pH was 2.88, which we can mark around here, 2.88. And we know that this is a titration reaction between a strong alkali and a weak base. So we can say that the straight portion of the curve is going to be from 7 to around 11 here. But at what volume is endpoint reached during this titration? Well, we know that endpoint is reached when complete neutralization occurs. So for complete neutralization, we know that same moles of sodium hydroxide and ethanoic acid must react. So for this, we can say that to find the volume, we can write volume equals to moles of NaOH during titration into 10 to the power 3 by concentration of the solution. We know that sodium hydroxide and ethanoic acid react such that same moles of both reagents react to reach neutralization. So we know that at neutralization, 1 times 10 to the power minus 3 moles of sodium hydroxide was used up. So what volume of sodium hydroxide represents 1 times 10 to the power minus 3 moles of sodium hydroxide? That will be the volume of sodium hydroxide at which endpoint was reached. So for that, we know that the equation is volume equals to moles 1000. The concentration is 1 times 10 to the power 3 minus 3 into 10 to the power 3 by 0.1, which is 10 centimeters cube. So we can say that this two points, so we can say that these 2 points represent the straight portion of the curve, and end of this titration is reached at a pH of 12.5, because this shows when pH, because this shows the situation of the solution after all of the sodium hydroxide was added into the ethanoic acid solution in the flask or beaker. So the pH of the end solution is 12.5, which is around here. So we can draw the curve to be like this. There, we have our curve. In part 5, we've been asked to find a suitable indicator for this titration reaction. We have 4 options. We have malachite green, thymol blue, bromophenol blue. We know that the pH of endpoint must be within the range of an indicator. So we can say endpoint was reached between 7 and 11, and only thymolphthalein contains the range where endpoint was reached. So we place a tick in the 4th box. So that is it for the 3rd question.